Our presentation is on the procedure for calibrating the supersonic wind tunnel at North Carolina State University. For this supersonic wind tunnel, the flow of air is altered by a block setting. By making pressure measurements at different block settings, we would know the limits at which the wind tunnel operates. We could also use the data to determine the flow conditions at the block setting. Furthermore, rather than pressure measurements, a second experiment was performed in which Schlieren imaging was used to determine the free stream Mach number in the tunnel. Under regular conditions, the air acts like a perfect gas, so we are able to use relations such as pressure equals density times R times T, and we can assume the air properties CV and Cp remain constant. In supersonic flight, the speed of sound is exceeded and a shock wave forms over the body. Across the shock wave, the atmospheric conditions, pressure, temperature, and Mach number change. For example, the Mach number after the shock wave is lower than the atmospheric Mach, whereas the stagnation pressure increases across the shock. The entropy of the airflow increases across a shock wave, so we cannot use isentropic laws to relate the flow on one side of the shock wave to the other. An assumption we can make is that the airflow across a shock wave is adiabatic. If we assume this, then we have thermodynamic equations to help us relate the conditions on either side of the shock wave. Using adiabatic flow relationships, substitution, and equation rearranging, we can relate the total pressure on either side of the shock wave to the Mach number of the incoming airflow. This formula was used with pitot tube measurements to determine the Mach number of the airflow for each block setting. Shown here is the test section, where the pitot tube is located. The compressed air from large tanks outside rushes down the tunnel from left to right. It takes approximately 5 minutes to recharge the system for the next 1 to 8 second test. The block setting is changed by turning the wheels shown here. Decreasing the block setting causes the flow to reach higher speeds and thus higher Mach numbers. This occurs because decreasing the block setting decreases the cross-sectional area of the tunnel upstream of the test section. This causes the subsonic flow in the tunnel to become supersonic right before the test section. The tunnel is equipped with another pressure port in addition to the pitot tube that measures the stagnation pressure in front of the shock wave. This experiment involves changing the block setting from 2200 to 800 while recording the pressures before and after the shock wave that forms on the pitot tube. The Mach number was then found using the previously mentioned equation. Because the flow is still supersonic and shock waves are formed, the same assumptions as before are required. Unlike the first experiment, however, Lab 2 utilizes Schlieren photography to take a picture of the shock wave formed in front of a wedge. In a basic sense, this method requires concentrating a light source into a single beam of light that will pass over the object in the test section of the wind tunnel. Because there is such a large density change in the air across the shock wave casts a shadow. The free stream Mach number, m sub a, can then be found through a relationship between the wedge angle, theta, and the angle of the shape that forms the object, beta. A constant standard value of 1.4 was assumed for the ratio of specific heats for air, or gamma. In order to conduct Lab 2, the block setting was again changed from 2200 to 800, while the change in the angle of the shock over a 10-degree wedge was observed. These angles can then be directly used to determine the Mach number in the wind tunnel using the equation on the previous slide. Pictures such as the one seen here were taken during each test. The angle was found by importing the picture into SolidWorks. In order to account for any angularity in the flow, meaning that the flow is not parallel to the line of symmetry of the wedge, the angles between the shock boundary and the line of symmetry on the top and bottom were averaged. Although this introduces some amount of error, the angles were similar enough that it is negligible. As it can be seen from the table and graph of the data from Lab 1, decreasing the block setting causes the Mach number to increase, reaching a Mach number of 2.65 at a setting of 1000. Therefore, over the course of decreasing the block setting by 1600, a 42.5% increase in the Mach number was obtained. This is significant considering that a range of Mach numbers can be reached without changing the amount of air or power required to supply the wind tunnel. The equation for the line of best fit is shown on the graph. This equation can be used in later experiments to calibrate the wind tunnel. Note that the smallest block setting, 800, only resulted in a Mach number of 2.37. This number does not match the pattern present in the rest of the data. Instead of increasing in Mach number, a decrease in Mach number with a large percentage difference from the line of best fit was observed. Therefore, this point was excluded when deriving the line of best fit. Shown here is the analysis of the pressure data to find the Mach number. Rather than using max pressure values, however, the Mach numbers were calculated with the values of the 98th percentile of both the stagnation and pitot pressures. As it can be seen from the table and graph, the data exhibits the same trend of an increasing Mach number with a decreasing block setting. Again, the equation for the line of best fit is shown on the graph. Note, however, that all of the data points were included when making this line. For the sake of comparison, the two tables for the analysis of the Lab 1 data is shown above. Except for the widest block setting, the Mach numbers resulting from the use of the max pressure values are consistently lower. Notice how there is a significant difference between the values for the 800 setting. In fact, there is about a 33.1% difference. One possible reason for this is that there is an outlier in the stagnation data for the 800 setting test. If this outlier were the maximum value of the stagnation data, that would explain why the max value analysis is affected by this data point, whereas the 98th percentile analysis filters it out automatically. So which form of analysis is better? To answer this question, more data is required. As shown above, the results of the Schlieren imaging show the same trend. The Mach number increases with a decreasing block size. Unlike the pitot data, whose resulting Mach numbers ranged from 1.8 to 3.31, the Schlieren imaging data resulted in Mach numbers from 2.22 to 3.56. Shown on the right is the original calibration curve for the supersonic wind tunnel. As shown by the intercepts for the 800 and 2200 block size tests, according to the manufacturer, the Mach numbers should be about 2.75 and 1.725 respectively. Therefore, the Mach numbers from the second lab are consistently higher than the original calibration data, indicating that the tunnel needs to be recalibrated. The data from Lab 1 also reinforces this fact, as almost all of the Mach numbers are higher than the calibration curve data as well. However, despite the differences in Mach numbers themselves, both the plots from Lab 1 exhibit the same curve as the original data, showing that the lab was successful. So, which form of analysis is better for the pitot data? To answer this question, it was assumed that the results of the imaging are the most accurate, since taking a picture of the shock wave is inherently more accurate than measuring data with pressure ports that may need to be calibrated themselves. Therefore, the analysis whose Mach numbers are the closest to the ones from the imaging is the more accurate method. As shown above in red, aside from the 2200 setting test and a tie at the 1400 setting test, the results of using the 98th percentile are the closest to the Schlieren imaging. Therefore, using the 98th percentile is the more accurate of the two analyses of the pitot data. It is still important to note, however, that the percent differences are relatively the same. Additionally, as described before, the majority of the data is higher than the original calibration data. Therefore, all of the data shows that the wind tunnel needs to be recalibrated. In summary, by measuring the pressures across the shock wave and by taking pictures of the shock itself, the free stream Mach number was calculated for each block setting. By plotting these Mach numbers versus the block setting, a calibration curve similar to the original one was obtained. The equation for this curve can later be used in future experiments to calibrate the wind tunnel. Despite the similarities to the shape of the original calibration curve, however, the data collected in these two experiments was consistently higher than the manufacturer originally designed the tunnel for. The data collected and the calculations made may have errors associated with them. A change in atmospheric conditions may affect the flow properties of the air. Our measurements are also dependent on the accuracy of the pitot tube used. Though all calculations should be checked to be accurate and free of errors, human error may have still be involved in calculations. For instance, the wheel used to change the block setting was not quantized, but rather continuous, and thus it was difficult to know for certain whether the block was actually at the desired position. Despite these sources of error, the labs were successful. The Mach numbers were obtained at each setting, and a calibration curve was obtained for the wind tunnel. Despite differences in the individual Mach numbers, all of the data indicate that the wind tunnel needs to be recalibrated.